Good morning. Today we will start the new unit, Polarization. The syllabus of this unit is given here. We have to discuss the elementary ideas about polarization, Brewster's law, double refraction, positive and negative crystals, quarter and half wave plates, production of plane, elliptically and circularly polarized light, and finally the optical activity. Okay. So we will start with the elementary idea of polarization. What is polarization? So in order to understand polarization, let's start with the light wave. So what is light wave? What should be your answer if somebody asks you what is light? So light is an electromagnetic wave, which means it have both electric and magnetic fields. These electric and magnetic fields are varying in two mutually perpendicular direction, and both these are perpendicular to the direction of propagation also. So electric and magnetic fields are the physical quantities which varying in light propagation. So simply we can say or our answer to the question what is light is it is an electromagnetic wave which having electric and magnetic field which are vibrating in two mutually perpendicular direction, and both these are perpendicular to the direction of propagation also. Okay, here you can see the picture of an electromagnetic wave. This picture may not be clear, so I will show you another picture. I'll show you another picture in order to understand the nature of electromagnetic wave, which is this is the electromagnetic wave. Okay, here you can see this ash color line. This ash color line represents the direction of propagation of the wave. It is marked as C, and this red colored arrow indicates the direction of vibration of electric field, and this blue colored arrows represents the direction of propagation of magnetic field. So you can see from this picture that the electric field is vibrating in the y direction, and the magnetic field is vibrating in the x direction. Okay, if this is y axis and this is x axis, so we can take this as z axis. So this both electric and magnetic fields are vibrating perpendicular to each other, and both these are perpendicular to this direction, that is the direction of propagation. So this is what a light wave, which is an electromagnetic wave. Okay, so let's go back to our previous part. Okay, so we know what is an electromagnetic wave or light wave. So light has both wave nature and particle nature. We can explain these natures depending on the experiments we are conducting using light. So we have studied this in your earlier classes, that light has both particle and wave nature. So the nature of this light wave can be explained that depends on the experiment we are conducting. For example, photoelectric can be explained only with the particle nature of light. It cannot be explained using the wave theory of light. Okay, similarly, the phenomena like interference, diffraction, which we have already discussed in our last units, can be explained with the wave nature of light. So the experiments we are conducting will determine the nature of the light, whether it is particle nature or wave nature. Okay, sorry, I can zoom this page to some more. Okay, but these experiments will never tell you about the nature of the wave. So from such experiments we can we can determine whether the light has particle nature or wave nature, but we cannot understand the nature of such waves, that is whether it is transverse waves or longitudinal wave. So no such experiments which tell you the nature of this wave, whether it is longitudinal or transverse. What is meant by longitudinal? Longitudinal wave, the particle vibrates, or the physical quantity which vibrates in the wave is vibrating in the direction of propagation of the wave. Or in the case of transverse wave, the physical quantity which varying is vibrating in a direction perpendicular to the direction of the propagation of wave. So that is the difference between longitudinal and transverse wave. Because both these types of waves can produce interference and diffraction, so we need a unique experiment to determine the transverse nature of the wave. Polarization is such a unique method for this. So we have one. There is no unique experiment which explains the nature of the wave of light. Polarization is such an experiment, that is, which will tell you what is the character of this wave, whether it is transverse or unique. So we have to understand what is polarization. So a light wave consists of both electric and magnetic field that we have already seen, which are perpendicular to each other, and these are together perpendicular to the direction of propagation. So if this is x-axis and this is y-axis, that is, this x and y-axis are lying in the plane of the paper. So this xy plane is in the paper, and suppose this is z direction, that is, this z direction is outward from the paper. Okay, we can represent it by a dot. We can represent it by a cross also, which means the direction is inward to the paper, inward to the plane of the paper. So I have represented the z direction as a dot here, which means the z direction is outward from the plane of the paper. Okay, so the electric and magnetic field is in the xy plane, that is in the plane of the paper. So if E is, that is E means electric field. If electric field is in the x direction, then magnetic field will be in the y direction, because both these are mutually perpendicular in direction. If this E is in y direction, then B should be in x direction, etc. Or if E is in this direction, the B can be, magnetic field can be either this direction or this direction, which is mutually perpendicular to this E direction. Okay, so we can have many directions of such E and B, because E can be in this direction. What is the condition is E and B lie in the xy plane such that E and B are vibrating in a mutually perpendicular direction. So this E and B must lie in the xy plane, and these are perpendicular to each other. So there can be E in this direction, in this direction, in this direction, in this direction, etc., etc. So there can be magnetic field perpendicular to this corresponding E's. Okay, so if we are talking about any phenomena about light, the physical quantity associated with every optical phenomena is electric field. So the interaction ordinary light source consists of large number of atoms. The vibration of these atoms produce the electric field in it. So these vibrations can be in any direction in the xy plane of the wave, which is propagating in the z direction. That is, the electric fields are vibrating in different direction in an ordinary light wave, but in a restricted plane. The plane of vibration of E electric field is restricted according to the direction of propagation of light wave. Such a light source is known as unpolarized light. That is, ordinary light source emits unpolarized light. What it tell you is that So we have seen every optical phenomena is associated with the electric field. Okay, so the electric field is produced by the vibration of atoms in the medium. Okay, so any ordinary light source is consists of large number of atoms, and the vibration of this atom is producing the electric field in it. And this can be, if this wave is this light wave produced by this ordinary light is propagating in the z direction, then the electric field can be vary in the xy plane, which means if it is electric field is varying in the x plane the x direction, then the magnetic field will be in the y direction. So we can talk about the electric field direction alone now, because every optical phenomenon is associated with the electric field. Okay, so the electric field direction can be this direction, can be this direction, can be this direction, or any direction, but it is restricted to this xy plane. Okay, so every E vector can be resolved into a combination of x and y component. Okay, so every E vector can be resolved like a, or it is a combination of x and y components in the xy plane. This restriction of this electric field in the xy plane is such that the wave is propagating in the z direction. Okay, so this is the direction of electric field. So the ordinary light is like this, that is it will have electric field varying in all direction, vibrating in all direction in the xy plane. So this will be the unpolarized light. So it will look like this. Okay, so this is known as unpolarized. So ordinary light source is a light source is a source of unpolarized light, or it emits unpolarized light. So this is the representation of unpolarized light, because it means it have electric field vibrating in all direction. Okay, all direction but restricted to one plane. The plane restriction arises because of the direction of propagation of the wave. Okay, if we can restrict this direction of vibration of electric field only along one direction, either x or y, we can say that light is polarized along x or y plane accordingly. So we can see this electric field is now in the xy plane. If we can restrict somehow the electric field in any single direction, either this direction or this direction or this direction or this direction, if we can restrict the vibration of this electric field in only one direction or only a single direction with some method, then that light produced is known as polarized light. If it is restricted to vibrate only along x direction, we can say it is plane polarized along x direction, or if it is restricted along y direction, we can say it is plane polarized along y direction. Okay, so as a transverse wave, electromagnetic wave can be polarized. Polarization is the distribution of the electric field in the plane normal to the direction of propagation. So we can define this polarization such that it is the distribution of the electric field in the plane normal to the direction of propagation. So the direction of field vibration is restricted to a plane which is perpendicular to the direction of propagation. Such a process is known as polarization. So we will get only a single direction vibration, field vibration. Okay, instead of many direction field vibration. So we can now see what is the representation, how we can represent the polarized and unpolarized light. So we can represent the unpolarized light in two methods. One method is this, this is the direction of propagation Z, and this is the direction of vibration of electric field in this direction, and this is this direction perpendicular to the plane of the paper. So this is unpolarized light because it can vibrate in different direction, or we can represent in this way. In this also it can vibrate in it vibrates in different directions. Okay, this arrow in this figure represents in the plane of the paper, and this dot represents perpendicular to the plane of the paper. Similarly, the polarized light can be represented like this, either this or this. That is, the vibration is restricted to in the plane of the paper here, and here the vibration is restricted to perpendicular to the plane of the paper. So if we are restricting the unpolarized light, if we are restricting the field vibrations of the unpolarized into a particular direction only by some method, then that process is known as polarization, and the light produced is known as polarized light. So this is the process of polarization. Now we'll look into this picture. So we have to understand two more terms about polarization. This plane of vibration and plane of polarization. Before that, I will show you one more picture, which is the representation of polarized and unpolarized light, which I have already shown you. So this is the representation of polarized and unpolarized light. So the first figure represents unpolarized light, in which the field is varying in different direction, and the second one is both these are unpolarized light. We can represent in either way, but when we are coming to the representation of polarized light, in the second figure only the arrow or the dot will remain. So that is the representation. Okay, now we will move on to the plane of vibration and plane of polarization. Okay, so we have to understand what is plane of vibration and plane of polarization. So plane of for that I will show you another picture. Plane of polarization. Okay, so this is that picture which will tell you the plane of polarization and plane of vibration. Here, this is the unpolarized light which is passing through a tourmaline crystal, which will produce a polarized light at the other side. So this is the polarized light in which the electric field is restricted to vibrate only along this direction. So this direction, that is the direction of this vibration, is in the direction. So the plane including the direction of vibration is known as, that is, it is marked as PQRS. PQRS, the box which represents the plane of vibration, that is in which the field is vibrating, is known as plane of vibration, and the plane which is perpendicular to this direction of vibration or the plane of vibration is known as plane of polarization. So this is two important terms related to polarization. Okay, plane of vibration and plane of polarization. Now we will discuss about the polarization by reflection and the law associated with this polarization by reflection, and for that let's go back to this textbook. Okay, so here polarization by reflection means we can see a picture here. So Malus discovered that ordinary light, when reflected from a plain sheet of glass, gets partially polarized. The percentage of polarization varies with the angle of incidence. At a particular angle of incidence, the degree of polarization is maximum, and this angle is called the angle of polarization. So it is Malus, the scientist Malus, who discovered that the ordinary light, when get reflected, this is ordinary light, which you can see from this representation, which is unpolarized, when falling on in glass-like sheet. This is the polarized light. It gets partially polarized. Okay, it gets partially polarized when it gets reflected from the surface. The percentage of polarization depends on the angle of incidence. It varies according to the angle of incidence, and at a particular value of this angle of incidence, this polarization is percentage of polarization is maximum, and that angle is known as angle of polarization, and we can represent it by I suffix P. P means P for polarization, I means angle of incidence. Okay, so we can look at the Brewster's law connected to this. So when an unpolarized light is incident on a denser transparent medium like glass or water from a rarer medium, which can be air, the incident light is partly reflected and partly transmitted. Here you can see from this picture. So this is glass. Imagine this is glass and this is air. So this is denser and this is rarer medium. So light is falling from this direction. This is rarer medium to the denser medium. So this is unpolarized light. So what will happen is some part is transmitted and some part is reflected. So here you can see this is IP, that is the angle of incidence. So the degree of, or the percentage of polarization, we have just seen from the Malus law that when get reflected, it will get partially polarized. So it will depend upon the angle of incidence. Okay, so it has shown in this figure. So this is angle of refraction. The reflected ray is partially polarized, as we have seen from the previous law. It is partially polarized. The degree of polarization depends on the angle of incidence. The reflected light is maximum polarized when the angle between reflected ray and refracted ray is 90 degree. What it says that the reflected light is maximum polarized. So this light is maximum polarized when the angle between this is reflected light and this is refracted light. When this angle between these two light rays is 90 degree, then this reflected light will get maximum polarized. Okay, so the angle of incidence at which the reflected light is completely polarized is called Brewster's angle or polarizing angle for a pair of media. Brewster proved that the tangent of angle of polarization is numerically equal to the ratio of refractive index, which is represented by mu suffix 2, of the denser medium to the refractive index mu suffix 1 of rarer medium. Okay, so what Malus is, Brewster's proved that the tangent of angle of polarization. So this is the angle of polarization. The angle of we can explain this again. The angle of incidence at which the reflected light is completely polarized is Brewster's angle, which we have seen just before. Okay, so when this reflected ray is completely or maximum polarized, then that angle is known as angle of polarization. Okay, or Brewster's angle. So the polarizing so what Brewster has done is that he has proved that the tangent of angle of polarization means tan IP, is equal to the ratio of refractive index of the denser medium, which is mu2, to the refractive index of the rarer medium, mu2 minus mu. This is Brewster's law, where IP is the polarizing angle at which the reflected ray gets maximum polarized. This is known as Brewster's law. Using Brewster's law and Snell's law, we can prove that when the angle of incidence is IP, the reflected and refracted rays are perpendicular to each other. That is, we have already discussed here that the reflected light will get maximum polarized when the angle between these two rays are 90 degree. Okay, so you can see that we are imposing here two conditions. Not imposing, if the light reflected from the surface is getting maximum polarized when the angle of incidence is angle of polarization. Okay, that is one thing. And the second thing is, it gets maximum polarized when the angle between these two is 90 degree. Okay, and Brewster said that, proved that tan IP, the angle of polarization, tangent of angle of polarization is the ratio of the refractive indexes of the medium. So from this, using the Snell's law, which is sin I by sin R, which is represented by mu2 by mu1. We have already studied this in our higher secondary classes, this Snell's law. So we have Brewster's law, tan IP is equal to mu2 by mu1. So right sides are equal for this. So we can write from this expression, tan IP is sin I by cos IP. So we can equate the left side. So we will get sin I by cos I is equal to sin I by sin R. Okay, so this is from this sin IB, the numerator is common, sin I, which will cancel each other. So we will get cos I is equal to sin R. Cos I is equal to sin R means this can be represented in terms of cos, that is cos 90 minus R. Cos 90 minus R is sin R. So since left and right side are in terms of cos, we can equate the angle. So we will get I is equal to 90 minus R, or I plus R is equal to 90 degree. So this is what Brewster's proved, that is the angle between the angle of reflection and refraction is 90 degree. Okay, that is I plus R. This shows that angle between reflected and refracted ray is 90 degree. So this is known as Brewster's law. Okay, so that's all for today's class. Thank you.